Hi everyone, I am Rosey Gutierrez, and today I will be presenting on the sufficient condition for differentiability of functions of several variables. Calculus is a fundamental branch of mathematics that studies how things change over time or space. In single-variable calculus, we learn about functions that depend on a single input variable f of x, such as the height of an object as a function of time, whereas it would be f of t. However, many real-world phenomena involve multiple variables, such as the temperature and pressure in a room or the position and velocity of a moving object. So to study such a phenomena, we need the tools of multivariable calculus, which extend the concepts of derivatives and integrals to functions that depend on several input variables. One important question we may ask about such functions is whether they are smooth or differentiable. That is, whether they have well-defined rates of change in all directions. This is simple to see at a glance into dimensions, as we can easily identify a line resulting from a function is smooth or if it has any of the non-differentiable characteristics as seen here. In this context, this theorem provides a strong sufficient condition for the differentiability of functions of several variables. It states that if a function has smooth, constant changes in each input variable, then it will have a really well-defined total rate of change that captures the combined effects of all the variables. This theorem is important because it provides a way to determine whether a function is differentiable at a point without having to explicitly calculate the limit definition of that derivative. So calculating the limit of a single variable function as it approaches a point is easy since we only have two directions to take into account. But can you imagine having to calculate the limit of a three-dimensional function? There are infinite directions to approach a point in space. So this theorem is a really important part of multivariable calculus with applications in physics, engineering, economics, and other fields. So let's explore the statement and proof of this theorem, and as well as give some examples. So as mentioned previously, the theorem states that if all the partial derivatives of a function exist and are continuous in a region of space, then the function is differentiable in that region. In other words, if a function has smooth changes in each input variable, then it will have a well-defined total rate of change that captures the combined effects of all the variables. So formally, let f of x1 to all the way to x of n be a function of n variables defined on our region R in n-dimensional space. If the partial derivatives of f exist and are continuous on R, then f is going to be differentiable in R. That is, for any point a1, a2, all the way to a of n in R, there's going to exist a linear transformation t such that f of x1 to all the way to x of n is going to equal f of a1 to all the way to a of n plus t dot x of 1 minus a of 1, x of 2 minus a of 2 all the way to x of n minus a of n plus epsilon x of 1, x of 2 all the way to x of n, where epsilon x of 1 to all the way to x of n is a function that goes to 0 faster than the distance from x of 1, x of 2, x of n to a of 1, a of 2, a of n as x of 1, 2 of n approaches a of 1, 2 to n. The linear transformation t is called the total differential of f at the point A, and it represents the best linear approximation of f near that particular point. In other words, if we let f of x1 to all the way to x of n be a function of n variables defined on region R in n-dimensional space, if all of the partial derivatives of f exist and are continuous in R, then f is going to be differentiable in R. Let's illustrate partial derivative continuity on a three-dimensional function. Let's consider the function f of xy is equal to x squared plus y squared, which describes the distance from the origin to a point xy in the xy plane. This Pringle function here is a simple example of a function with two variables, and it has some really interesting geometric properties that we can explore using partial derivatives and continuity. The partial derivative of f with respect to x is given by rond f over rond x, which is equal to 2x. This means that the rate of change of f with respect to x depends only on the value of x, and it's equal to twice the value of x. Geometrically, this tells us that the slope of the mountains and valleys of the function along the x-axis increases linearly as we move away from the origin. In other words, as we move horizontally away from the origin, the function gets steeper and steeper. Similarly, the partial derivative with respect to y is given by rond f over rond y equal to 2y. This means that the rate of change of f with respect to y depends only on the value of y, and it's equal to twice the value of y. So geometrically, that tells us the same thing as f of x. It will tell us that the slope of the mountains and valleys of the function along the y-axis also increases linearly, and as we move away from the origin, we are moving vertically away from the origin. The function gets also steeper and steeper. So now let's consider the continuity of the partial derivatives of f. Since the partial derivatives are just linear functions of x and y, they're going to be continuous everywhere. This means that the function f itself is also going to be continuous everywhere. And we can visualize this by imagining a smooth round hill that rises up from the origin in all directions. In summary, the function f of x of y equals x squared plus x. F of xy equals x squared plus y squared provides a simple geometric example of partial derivatives and continuity. The partial derivatives tell us how the function changes along those different directions, and their continuity ensures that the function is smooth and well behaved everywhere. Let's do two examples using this theorem. Let's determine the differentiability of the function f of xy, x squared, y cubed. We need to check if all partial derivatives of f exists and are continuous. The partial derivative of f with respect to x is rond f over rond x, which is equal to x, and the partial derivative of f with respect to y is going to be rond f over rond y, which is 3y squared. Both of these partial derivatives exist for all of x and y. Additionally, both derivatives are continuous functions. Therefore, since all the partial derivatives rond f over rond x and rond f over rond y exist and are continuous, the function is going to be differentiable in its entire domain. This means that for any point a, b in the domain of f, we can find a linear transformation that approximates f near that point. And that linear transformation is also known as a total differential, which is given by the differential function rond f over rond x dx plus rond f over rond y dy, which is 2x dx plus 3y squared dy. So we have shown that the function f of x squared plus y to the cube is differentiable everywhere, and its total differential is going to be given by differential is equal to 2x dx plus 3y squared. 3y squared. And here's another example using an exponential function with sine, cosine, and Euler's constant using that same principle. So let's go over some assumptions and clarifications for the theorem. If f of x 1, 2, all the way to x of n is a function of n variables defined of a region R in n-dimensional space, that is our first assumption. We're also assuming that our partial derivatives of x exist and are continuous in R. This theorem only provides a sufficient condition for differentiability, not a necessary one. So that means that if the assumptions of the theorem hold, the ones that we just listed, then we can conclude that f is differentiable in R. However, it's possible for a function to be differentiable without satisfying the assumption of the theorem. So we can use this to prove a function is differentiable in R, but we cannot use this theorem to disprove it. So take this function for example. It's smooth everywhere to our eyes, but the theorem will hold, as you know, the partial derivatives of the function do exist. But it's going to be easy to spot too that x and y on the function itself, not on the visual, that if both x and y are 0, then the function is going to be discontinuous at 0 because it's going to be undefined. That's why this function has to be represented as a system of equations for the function and the point 0 in order to be considered continuous as a whole. So we can definitely use this theorem to prove that a function is differentiable in R, but we cannot use it to prove non-differentiability. So here is the proof of the theorem, but in the interest of time and to be respectful of those who are also presenting today, I'm not going to go over the whole thing since it's on the slide in its entirety. I know Honors uploads these presentations on YouTube channels, so if you're interested, be sure to check it out, and you can pause in your convenience as well. Here are my sources and image, icon, and vector asset credits. And I just want to thank everyone for your time. I want to especially thank Professor Sahedani for being an amazing teacher and mentor and for giving me this honors contract to be able to graduate with my honors certification. Please let me know if you have any questions, and thank you again.